The trooper is here, or the cop. And you are driving at 45 meters per second when you pass this guy. And you keep driving, right? 1 second after you pass the cop, the cop is going to accelerate at 3 meters per second square. How long does it take for the cop to overtake you? So obviously, we're gonna say that it meets you here. So the cop is here, is gonna travel a distance, let's call it D. That's the distance of the cop, by the way. That's how much it has to travel to catch. But this piece of information is important though. First, before the cop starts traveling this distance, the car yourself, you were moving for 1 second by yourself. Can somebody tell me if you are traveling at constant speed of 45 meters per second, in 1 second, how much do you travel? So you in 1 second at 45 meters per second, comma, what is the distance that you travel? How much you move? It's constant speed. Hmm?
45.
Yeah, 45. Distance of speed times time. Perfect. So you move 45 meters. So you are here. All this is so if all this is D, how much is this? This is D, and this is 45. How much is this? Right or not? Yeah, yes.
That's right.
Yeah. D of the cop. What is this? We can find it. The cop was hidden. So it wasn't moving. What's the initial speed of the cop?
45?
No. Zero.
Yeah.
Zero. That's the initial speed of the cop. So it's accelerating. What equation do you use to find the distance of the cop? So you have initial speed times time, plus or minus, plus because it's accelerating, 1/2 AT squared, right? We have this equation here. But wait a second. 0. I have A. Huh? One half, which is all right. I have D of the cop. this. But the car yourself, you were still moving. The same time that the cop takes to catch you. That's the equivalency. The time you keep moving after 1 second is the time the cop takes to overtake you. So d minus 45 for yourself. U. D of the cop minus 45 is equal to, because you are going at constant speed, I have D. There you are. 1.5 t squared minus 45 equals to 45. Huh. 1.5 t squared minus 45t minus 45. You know what? We can apply quadratic formula, right? Yeah. Let's put it here. Remember though, a quadratic equation, quadratic formula, will give you two solutions, but we cannot have negative solutions. A, B, C. So negative B minus B plus or minus square root of B squared is minus 45 squared is just 45 squared, but minus 4 times 1.5 times negative 45. Because negative 45 is will become positive. Over 2 times 1.5. And let's take a look at the square root. Let's see let's see the discriminant. I want to see if that gives us, and it will give us a large number, right? So 270. Okay. The square root is 48. Round. All this is 48. So I cannot take the negative 48, it has to be positive. So 45 plus 48 divided by 2 times 1.5 is 3. 31, exactly. After 31 seconds, after the car, after the 1 second that the car moves by itself, you have to specify that. Yeah, so approximately half a minute. Do you understand? Do you see what's going on?
Yes.
Yes.
Right? So that's an interesting problem there. And that's a more type of problem you can get combining constant and accelerating accelerated motion. See if I have another one before I give you guys that break. Oh yeah. By the way, guys, the answer you can find in this, I mean, it's also in the slides, but it's a bit different the way they did it. Let's put one like the one that you guys have in the web assignment or something. Except for a 20. A particle, find a position. There is a with falling objects, there are more examples. I'm just seeing if there's actually let's do this because I wanna specify something about this problem here. starting from rest. Down there for a bit. They give you that a car, sports car, accelerates from rest to 50 meters per second in 8 seconds. So a sports car starts from rest to change the numbers, by the way, it's not the same, okay? 48 meters per second in 8 seconds. And there are different parts. First of all, they're asking you to find the magnitude of the acceleration. When you start from rest, what's the initial speed?
0.
Yeah. The final is 48 and the time. So, final, initial, accelerates. Sorry. So the acceleration is 6. Okay. So assuming the acceleration is constant, find the distance after 10 seconds. All right. We use this equation. The distance after 10 seconds. So okay. We use the equation. You can use that as well. D equals to initial speed times time plus or minus 1/2 AT squared. This is 0 because initial speed is 0. It's accelerating, so it's plus 1/2 acceleration 6. T squared was 8. 32 times 6, 12, 18, 192. What is the speed of the car after 10 seconds? That's a problem from the web of science. You see how simple this problem is, right? So then you want to find the final at 10 t equals to 10 seconds. Well, that equation, then, right? The final equals to the initial plus a delta t. Initial is 0, acceleration is 6, time is 10, 60 meters. All right, so exactly 7:30, that's perfect. And you guys, 5-minute break. We're gonna do falling objects, and that's it for chapter 2. Not bad. So, but I mean, I'm gonna do a couple of, there are a bit more tricky problems in falling objects, so I will go over at least 2 or 3 of those. And then, guys, that's it. I'll leave you guys time to finish with your homeworks and stuff, okay? I'll be here, you have a question.
Okay, so you want us to come back at 7:35?
Yeah,
Okay.
okay?
Yeah, that's okay.
All right, guys. What we have left right now to do is just the application of what we've been discussing today in falling objects. Now, in the slides, they start with a very important result from Galileo that was proven in the absence of friction, absence of air, in the moon. What happens if you release two objects from the same height? Now, let's say we have 1 kilo of iron and 1 kilo of cotton. Or they can be at different masses, right? You can have iron and cotton. Forget about the mass. What Galileo said is that regardless of the mass, those objects should reach the bottom at the same time. Now, he didn't have equations to prove his argument, but he was right. The person who supported that with math and with theory was Newton. When he studied gravity as a force, which is what we will cover in chapter 5. But pretty much what you have to remember is that every object on Earth or in any planet and with some gravitational field, which we call gravity here on Earth, will tend to fall towards the center of the planet, towards the ground. And that's because of gravity. So what is gravity? Gravity is not really a force. I mean, the gravitational force is a force. Gravity is a property of a given object, in this case of our planet, which exerts a force upon us. And it makes us accelerate towards the ground, which is why my pen would fall towards the ground. So, what Galileo said is that if you have an object, this object will accelerate towards the ground due to gravity. And we know, well, I mean, which you can say this is delta y, vertical, right? Falling objects. What we know is that depending on the latitude, if you're in the equator or on the poles, or say, for example, in Canada, and if you compare with the value that you can estimate or measure on the equator, the value of gravity can be not different, but 9.8, 9.81 meters per second squared. But in general, the accepted value is equal to negative 9.8 meters per second. So normally we just say 9.8, but we write negative to specify that it's going always on the negative y direction. That's the first thing. Here is where things can be a little bit confusing. So I want to show you two ways that you can stay with the one that you feel more comfortable. Whenever you are solving a problem of falling objects, make sure that you understand what's happening first. So I can throw a ball, goes up and down. You can accelerate a rocket. The engines shut down and then it falls. But then we have to consider some inertia, which we're going to talk as well, solve a problem like that. But in general, when objects are falling towards the ground, we say that they are accelerating towards the ground. So all our equations of motion work. The only thing is that now we have the value of the acceleration, which is always constant, 9.8 meters per second squared. But also, we have to change the delta x to delta y. But we have initial, final speeds and time. So that is always the same. So let's write down here the equations of motion. The first one was the final velocity of speed, right? On y. When we do two-dimensional motion, that notation is going to be very important. So in two dimensions, we're going to have x and y. So you already get used to it. Is b initial on y plus or minus. So this is what I'm talking. This is where things can be a bit not confusing, but where you have to be careful. If the object is falling, because it's falling, you should use negative. But wait a second. Gravity is negative. Negative and negative is positive. So the way I learned this student was that if the object is falling, is gaining speed. Increases. Therefore, the final on y is equal to v initial on y plus, and then you just put 9.8 there. So you can say G just 9. And that will be for every other equation. With delta y, which if we are dealing with the scalars, it's just the height is equal to v initial on y times time plus or minus 1/2 gravity square. See why I did that? I changed A for G. Then you also have that V final on y squared equals to V initial on y squared plus or minus 2G delta y. So everything changed with y, but now I have the value of gravity, I have the acceleration. Okay. So again, when I do the problems, you will see how I'm going to be doing them. You can either, let's say the object is falling, so you just keep that negative, right? But the gravity you use, since you are keeping, since basically when you do this, so for falling objects, you use this, you're using the vector form. If you use the vector form, remember that G is negative, so negative and negative, that becomes a positive. If you use the scalar form, then you just say, oh, the speed is increasing. Have to use plus. I think both ways are correct. One deals with the direction, the other one deals with the physics. So you understand what's going on. Okay? Because trust me, the problems are not just gonna be I throw or I release. By the way, when you drop something, when you release something, the initial speed is 0. They can give you I throw something and it comes down again. Right? As we are going to do, don't worry. So if I show you guys the slides on this part, of course, that with Galileo and the experiment in the Tower of Pisa. Just talking about objects falling at the same time. Let's start with this. What happens to the acceleration of a ball after you throw it upward in the air? increases, decreases, increases, decreases, decreases, increases, or remains the same?
It increases.
And decreases?
The acceleration. What's the acceleration of a ball in the air? If you throw right now a ball, why does it comes back to your hand?
Gravity.
Why it falls back?
Because of gravity.
And gravity changes? Does gravity change? Does gravity change?
No, gravity doesn't change.
So it remains the same.
Yeah.
You got it's a tricky question. All right, it remains the same. Okay, there. What happens to the speed now? After you throw it upward in the air.
Increases and decreases?
When you throw it up,
Yeah, it increase.
It decreases.
and then increases when it falls back.
Yes.
Oh. Okay.
Right.
Okay.
A ball will decrease first, and then it will increase as it comes up to your hand.
Okay.
See how it says neglect air resistance. We're gonna neglect that. All right. So skydivers, right? If you the only thing I have done paragliding, so it's not the same. Bungee jumping, yeah, actually bungee jumping you feel it. So when you jump, right, and if you ignore air resistance, right, both in this case they give you both skydivers will fall with the same acceleration. Does the difference in the speed stay the same through the fall? What do you think? Does the vertical distance between them stay the same through the fall? So the difference between their speed, guys, depends on gravity. Whenever you are falling, whenever you jump, parachuting, no, it's not a good example because parachuting, you have the parachute and it makes you slow down. Skydiver is like you go with gravity, right? So let's say you jump and you're skydiving. What can you say about the difference on speeds? Remember, the difference on the speed depends on gravity. And what can you say about the difference on the vertical distance? The difference between speeds.
Will it depend on the density or no?
No, forget about density because we're neglecting mass and air resistance for now.
Okay.
So as you fall, remember that equation B final equals to B initial plus or minus gravity times time. For equal time intervals, the speed difference will always be the same. Okay. What changes is the vertical. Because the reason why the vertical covers array as you go, right, is because, guys, if you see the equation here on the board, can you tell me what type of equation is this? I want to point it. What type of equation is this one here? If you plot y as a function of time, so y on the y-axis, obviously, and t on the x-axis, what type of graph is this? It's a quadratic equation, it's a parabola. So if you remember from algebra, right, the vertical starts becoming bigger and bigger. Not like an exponential, but the vertical distances are always incrementing. Right? So that's how you know that the vertical distances are going to increase. They don't remain constant. Why does the speed remain constant? Because the speed is linear. So the speed is a line. So the slope is always constant. That's a math way of explaining things. The physics way will be basically that the difference of speeds depends on gravity, and gravity is constant. Here depends on what? The square of time and gravity, so that changes. Plus you also have the initial speed, right? So there you are. Remember guys, these are conceptual questions that are not necessarily going to be asked, but it's good that you guys learn some of these concepts because so you understand when we do the problems why I keep things the way I do, why some things are kept constant, what assumptions we can apply in a given problem. This is a problem I want to go over with you guys. Because falling objects, guys, if I just do one object falling or blah, it's the same as what we did before. But this one is more interesting. You probably have done this in algebra when you guys did a vertical motion, right? But I want to do it in a different way. I want to do it the scalar way. So I want to break down the motion in two. So let's read the problem. It says that you are in the top of a building 50 meters high. Like in average, you're talking about 20 floors, 20 stories. And you are throwing a ball at 20 meters per second straight upward. I'm going to ask you to find how long it takes to reach the ground and what's the speed of the ball when it reaches the ground. Hint, it's not 0. Let's do it. Look, I know that if you have done this before, you probably were told to assume gravity equals to 10. Unfortunately, I cannot, maybe in my tests, I might let you do that. But for the web assign, don't do that because it will throw you off. So you have to use gravity 9.8. Of course, if gravity 10 makes things easier, but we can't, right? So gravity 9.8, that's always constant. He was 50 meters high, and then he threw a ball at 20 meters per second. So let's study the motion, let's see what happens. Since we can use the same equations, it's not going to be that something very different to what we did before. But again, there are some assumptions that you need to understand. So we are, or he is here. And then he throws a ball with 20 meters per second. And then the ball goes up, it reaches a maximum height. And lands here. And this is 50 meters. And don't forget always, gravity So first, let's analyze the motion going upwards. It goes up and eventually reaches a maximum height. Can somebody tell me what's the speed of the ball at the maximum height? What's the speed here? That's
Is
what?
it,
Yes.
I was gonna say, is it 20?
No.
No.
When you throw something, look, you're seeing that, right? My pen falls down, so it cannot be 20. 20 will keep going. So it goes, reaches the maximum height, and then falls back. So what's the speed when the pen is here?
0?
0. Yeah. 0. Initial, final, etc. So you can find how high it went. Yeah. And find this. I'm gonna put this delta y. I can put h1. I don't have time. Oh, that's good. So I don't have time. I have final speed 0, initial 20, and I have gravity. Which is the equation that you must always look at whenever you are not given time? This one. No time, no problem. B final on y squared, B initial on y squared, plus or minus 2g delta y on h. B final is 0. B initial is 20. Okay. Let's do both ways, scalar and vector way. Since you are going up, you take the positive, but gravity is negative. So it will become minus 9.8 times delta y, which is what you want. The scalar way will be, the ball is going up. So the final speed is less than the initial. The only way that can happen physically is if this is minus. Right? I mean, it makes sense, right? 9.8 times delta. If gravity was 10, it would be much easier, right? I know, but that's just how it is. So I find how high. 400, 19.6. Should be approximate 20 point something, let's see. Well, if I look, this is a chapter where we both agree with the other professor. 1 sig fig, 3 sig fig, so this should be 1 sig fig, right? If you follow it through, perfect. But we're not gonna be, except for the first exam where this exam about chapter 1, but we're not gonna be dropping points for not, for example, if you put 20.4, it's fine. But if I'm straight with sig figs, this will be 20. So I know that this went up 20 meters. Now the ball is coming down. How far? The ball is here, right? How much is the height in the downward motion? We need that to know how long it takes to reach this point. We need this total height. What is it? Look at the figure there.
No.
That's 50, right? And what's missing?
So it would be 70?
70. Yes. So this is all 70. Okay. Before we go into the downward motion, that's good. We need to find the time it takes to go up. Because I found the height. We needed that. The time to go up, we have initial, final acceleration. Well, V final on Y is equal to V initial on Y. It's going up, it's losing speed, minus GT. This is 0 equals to 20 minus 9.8. If I'm again strict with 6 feet, this will be 2 seconds. That's the time to go up. Now, I have the height. You guys told me already, that this is 0. So you know what? This becomes a free-falling motion. Free-falling motion is this. It's when you let go of a mass or anything. In a free fall motion, the height is always equal to 1/2 GT squared. Because the initial speed is 0. So 70 and I only take the positive because you cannot have negative times. So that's what? 3.8 seconds. Well, again, so to the question, how long does it take to reach the ground? 4, don't forget 2. So it touches the ground or it reaches the bottom after 6. Do you guys understand?
Yes.
Yes? All right. Well, now I want you to tell me what's the speed when it reaches the ground. So, and again, it's not simple. What's the V final? How will you find the velocity, the speed, as it reaches the ground? Look at the downward motion. You have the initial speed, you have the height, and you have the acceleration. You need to, you can use time as well, but it's practice using this. Okay, so let's see if I had a whole board, but no, the camera. Let's erase what? I mean, you already know that. I put it there. I want to erase this part, okay? I mean, it's recorded, but let's delete this in here. So if I want to find this one here in the downward motion, you will use the final is the initial, which is 0 squared, plus delta y. very important that you know what's happening, right, in the problem. $37 meters per second. So, I mean, these ones, these problems that we have done so far, don't require a lot of calculus, right? I'm gonna do one now, because now we can do, I mean, we did a few in the examples with the slides, but there are a couple, one in particular I wanna go over, that I asked in exam number 2 as well last year. Similar to the web assignment anyway, but that one will require some a combination, calculus and the equations of motion as well. Okay. So see how important it is to define your variables, to picture what's happening, to keep it organized, the units and all that, right? Also, as you can see, we are not making you guys do conversions so far, like everything is in meters per second, okay? All right, so this is one other problem. Somewhere. There it is. So you're going to be given